So welcome, everyone. Thanks for joining. A pleasure to be speaking to you today. A great conference. So I'd like to introduce myself. My name is Rich Hagarty. I work at IBM. Spent most of my career as a software engineer. The last couple of years as a developer advocate here at IBM. I'm based in Austin, Texas. In my role as a developer advocate, I get to talk about open source software, specifically around cloud native Java technologies. So I'd like to start with a couple of quotes from a recent poll, which I think is a perfect segue for my talk today. This poll is asking companies about the state of Java in the enterprise. The first quote you can see that is good news is that Java is not only here to stay, but the investment is going up. The second quote is around how companies want to modernize into cloud native technologies, which means distributed architectures like microservices and serverless. But as a Java developer, we know that's harder, that's easier said than done, especially when it comes to performance. So how do we get there? That's what the talk today is about. So as the title indicated, this is about JIT as a service. Just to level set, I know everyone here is a Java developer, so they all understand JVMs and JITs, but just to level set again, JVM is the Java virtual machine that executes your Java application, and it does that by interpreting the code byte by byte. To improve that performance, it has the access to a JIT, or just-in-time compiler, which is a dynamic compiler that will take that code and make it into machine code so that it's optimized and runs better. So the agenda for today is we're going to talk about the problem with Java on cloud, specifically around distributed architectures like microservices. And the reason for that is the JVM and the JIT, which are great technologies, been around for a long time, but there are some good and some bad, specifically when we're talking about moving to the cloud. And then we'll finish with the solution, which is JIT as a service. And we have a nice demo at the end. Hopefully we can get to that. So Java on cloud, is it a good fit? So let's talk about a little bit first about your typical Java application, your legacy Java app. That was running as a monolith on a dedicated server on-prem, definitely with plenty of CPU power and memory, never went down, very reliable. We had to update or refresh that very infrequently, so it always stayed up. That was the state of Java applications, say 10 years ago. So now we want to move to the cloud. So that same monolith application, we've broken up into many microservices, all running in containers, managed by some cloud provider and Kubernetes. And we have auto scaling, which means we could scale up more and more instances based on demand, actually scale up and down based on demand. And what are the motivations for doing this? Well, once we get off-prem, we have less infrastructure to maintain and manage. It provides us more flexibility and scalability. It's easier to roll out new releases because when we break that monolith down into loosely coupled microservices, we could update individually those microservices without affecting others. So it's easier to do that. And also, once we're on the cloud, we can now take advantage of all the latest, greatest technologies that are coming out. And we all know that the cloud changes constantly with new, better ways to do things. And ultimately, from a company standpoint, we think we're going to save money. But what about performance, right? That's the big key. So we need to balance the cost versus performance. And as far as performance and cost go, there are two main variables. It's your container size and the number of instances that you're running. On the cloud, it's all about resources used and getting the performance you need. So graphically, let's take a look. We have performance along the bottom. We have costs on the left-hand side. This first example shows that we have not allocated enough space for each of our containers, and we're not scaling efficiently. So cost is very low, but our performance is unacceptable. So we may decide, let's go ahead and bump up the container size. We're still not getting the right number of instances, but the cost is going up and performance is getting better, but still not acceptable. So this is basically the worst case scenario, or from a company standpoint, this is the worst case scenario. We're making our containers way too big. We have way too many instances running to handle the peak demands of our customers. So from a customer standpoint, performance is great, but we're spending way too much money. So our goal is to get into this bottom right quadrant. So this is a sweet spot, but it's very hard to get right. And there's a ton of Java innovation around trying to solve this problem. So you may have heard of GraalVM, Crack, Quarkus, Micronaut, Helidon. They all seem to have an answer to this problem. But why is this so hard? So to better understand, we need to go over some background on how Java applications execute. So we're specifically going to talk about the JV and the JIT, the good and the bad. So the good, the JVM makes your code device independent, meaning you can write once, run anywhere. It's got over 25 years of constant improvement. The JIT produces very optimized machine code. The JVM uses profilers to look at your code dynamically as it's running, and it can isolate and figure out the right code to optimize. It has very efficient garbage collection. And because of all that, the longer it runs, the better it runs. Right? The JVM collects more and more profile data, and it compiles more and more methods until you get to a very optimized state. The bad side of that way of doing things is that initial execution run is interpreted, which is relatively slow. Those hotspot methods that are compiled by the JIT, they have to be identified, and the compiles have to take place. And that causes CPU and memory spikes. Those CPU spikes cause lower quality of service. Your memory spikes cause out-of-memory issues, including crashes. And the end result is we have slow startup time and we have slow ramp-up time. And the difference between the two is the startup time is the time it takes to load all your libraries to run your application. And the ramp-up time is the additional time needed by the JIT to compile all the methods that need to be compiled to make your code optimized. So here are some graphs to show examples of what's going on. Let me get my cursor here. Get a pen. So the left side here, we see the CPU spikes associated with those JIT compiles. So this is at startup. So all these compiles are happening at the beginning, and you can see the spikes associated with that. And they're going to continue on until we get to some steady state. Same with memory. You can see the spikes needed to handle those JIT compilations. Again, they're going to be happening at the beginning, and then it's going to get to a steady state. So again, let's talk about that cost versus performance dynamic we have to work on, finding that sweet spot. So obviously we want to have right size provision containers. We don't want to waste resources. We want to be able to have an efficient container that can compile everything it needs, but not waste space. And we need to have well-behaved, efficient auto scaling. So let's revisit our two variables. So the pain points with container size. How do we provision our containers when we have activity like this with the CPU or the memory and the CPU, right? Basically what we're going to have to do is we're going to have to over provision to allow for these, to avoid out of memory issues going forward. So it'd be nice to set our container at the steady state, but we need to be able to handle these spikes. Again, this is very hard to get just right because the JVM is non-deterministic. So you can run the same application or the same container multiple times. You'll get different spike levels at different times. As far as scaling, the major pain point is that slow startup and ramp up times. Right? Typically on horizontal auto scaling, you set thresholds based on CPU levels. These CPU spikes can actually cause the autoscaler to incorrectly launch additional instances. So basically, it's going to get false positives. It's going to say, "Oh, our container is running at over 50%. Let's launch another one." But all it was really doing was compiling. So you're going to be thrashing about with your scaling. So in order to solve this issue, we have a goal. We have to minimize or eliminate our CPU and memory spikes so we can reduce that container size. And we also have to improve our startup and ramp-up times to improve scaling efficiency. And the solution I'm proposing is JIT as a service. So what does this mean? So basically, the JIT as a service, we're going to decouple the JIT compiler from the JVM and let it run as an independent process over here. Right? So we're offloading all those JIT compilers from the JVM and doing it remotely. And it's communicating over the network. We're going to treat the JIT compilation as a cloud service. This is also the beauty of working in Kubernetes is this is all going to be managed by that orchestrator. And for resiliency, the JIT still is going to be available to the JVM, but it's not going to be used. As long as that communication is open with a remote JIT, it won't use that internal JIT. So where do you get this JITServer? It is a feature that is available now, and it's open source. It's under the Eclipse OpenJ9 JVM. It's also referred to as a Samaru cloud compiler when used with the Samaru runtimes, which I'll get to in a bit. So I'll use those terms interchangeably. The OpenJ9 JVM combines with the OpenJDK to form a full JDK. And it's open source, and here's a link to the GitHub where you can contribute if you want. Let's talk a little bit about OpenJ9, the history of that. So it was designed from the start to span all the operating systems needed by IBM products. So this was an IBM JVM that was created over 20 years ago, 25 years ago. It was called the J9 JVM. It was open source to Eclipse around a little over 5 years ago. So the background was that IBM recognized how popular Java was, and they wanted to make sure that Java ran on all of their supported devices. That could include handheld devices to mainframes, correct? So it has to handle constrained environments or even memory-rich ones. So it needs to be very modular. It is renowned for its small footprint, fast startup and ramp-up time, and it is the core of the WebSphere and Open Liberty platforms. So there's a ton of large enterprises running all their Java apps on that environment. So OpenJ9 has been around for 5 years, but the J9 JVM has a lot of history there. So here's some comparison charts with the OpenJ9 JVM versus Hotspot, which comes default with the Oracle JVM. So OpenJ9 is in green, Hotspot is in orange. As you can see here, it can have faster startup time, a smaller footprint after startup. It ramps up faster in the cloud than does Hotspot, and it has a smaller footprint at peak loads. So we talked about Samaru runtimes a minute ago. So OpenJ9 comes with, it can be installed with the IBM Samaru runtimes, which is IBM's distribution of the OpenJDK. So it is available at no cost. It's high performance, cloud optimized, runs on all the major platforms. It's ready for development and production use. IBM Samaru runtimes comes in 2 editions, the difference being some licensing and supported platforms. And again, it's a default Java for Liberty, Open Liberty. Hopefully some of you have heard of that. That's a Java runtime. And for WebSphere Liberty. A lot of folks ask, so why does IBM have their own distribution? Well, they're not alone. There's a number of new distributions coming out over the last couple of years, basically to not compete with, but as an alternative to the Oracle distribution, especially when they're changing some licensing and things like that. So basically the distributions are to protect their customer base. So they're saying, get your Java from us. We'll support it on the environments that we support. So for example, Red Hat build of OpenJDK is tuned to run really well on RHEL. The Microsoft one supports running Java on Azure. And they obviously support their customers in those environments. So the IBM version is the same. There's another alternative. It's called IBM SAMR runtimes. So what are the advantages we get from running the JITServer for those JVM clients? So one, provisioning. Remember I talked earlier, I showed that graph. How do you provision when you have to handle those spikes? Well, if we eliminate those spikes, provisioning becomes very easy. We only have to consider the needs of the actual application. Performance, we're going to get that ramp-up time sped up because the JITServer is going to basically offload all that CPU power that's needed is going to be handled there, not from the client JVM. And with reduced resources, you're obviously going to save costs, right? So we're going to have smaller we're going to have smaller container sizes, and we're going to have more efficient auto scaling. So we're only going to pay for what we need. And it is resilient. Again, if the JITServer does go away, that communication goes away, the JVM could continue to run and compile with its own local JIT. We're going to show some performance graphs here. So the first test is going to be showing how we can reduce application density. So we're going to take a look at a Red Hat OpenShift environment where we're going to be trying to run 4 different applications running in containers with multiple instances. So here's a graph that's a little confusing, but I'll try to explain it the best I can. The top graph is the top section is without using a JITServer. So the applications are color-coded. For example, the yellow here is the Acme Air monolith. And you can see we have 8 instances running, and we've allocated 500 meg for each instance. And those, the size of those containers was tested to figure out the most optimum value for that. And as you can see here, to host all of the instances of the 4 applications, we require 3 nodes. Now let's take a look at using the JITServer. The JITServer here is shown for each, there's 1 per node servicing all the clients on that node. And you can see the JITServer is rather large here. It's 1200 megabytes. And it's the largest container in that node. We still have the same number of application instances running. For example, the Acme Air monolith still has 8 instances running, but we reduce our container size by 50% in this case. Overall, we're able to reduce each of the application container sizes down to the point where we can remove one of our nodes. So we've just saved 33% of our cost. And if we're wondering about performance, as you can see, the orange is without JITServer, the blue is with, and basically we're getting the same performance. Well, we get the steady state. It's basically the same. Again, using 33% less resources. Now let's talk about horizontal pod autoscaling. In this case, Kubernetes. We set up our autoscaler to trigger once we have average CPU utilization over 50%. Again, the orange is without the JITServer and the blue is with the JITServer. So as you can see, wherever we plateau and we dip down, it's indicating to the autoscaler we need to start another pod. And as you can see with the JITServer, our dips are less and we ramp up a lot quicker, right? The spikes are less severe. They're going straight up faster. And when we get down in these low dips, that's where the CPU utilization is going to really be taxied, trying to load up that new instance. And that's where you get those false positives, right? So the less of those we have, we're going to have less risk of tricking our HPA, our horizontal pod autoscaler, into thinking that we need to get another instance running. So with that, let's start a demo. Let me go ahead and stop this screen share, not the screen share, but the presentation. Okay. Bring up a slide real quick. Hopefully everyone can see this. This is what we're going to be showing today for our demo. We're basically going to be running this this Open Liberty Acme Air application in 3 different containers. The first version is going to be running at 400 megabytes. The second version at 200 megabytes. The third version will also be limited to 200 megabytes, but it will have access to a JITServer. The rest of these boxes are to support the application. So the MongoDB is needed by the application. InfluxDB and Grafana are used to store the metrics that we're going to be showing. And we're going to be running JMeter to simulate HTTP data loads to the applications to see how they fare. So let's go out to our demo system. And let me start up. Let's start Grafana first. Then we'll start Influx, which is our database storing our metrics. So now we'll get to the actual container pods that are going to be running. Let me see. I got to remember which order. Okay, let's start up Mongo database, which is needed by the application. Now I'll start up the JITServer. Then I'll start up Prometheus. Okay, so all of our background services are ready to go. I'm now going to start up Acme Air, our 3 containers. So if we take a look at that, hopefully you can see this. It's large enough. Let me move this over a little bit. So I'm running Docker 3 times. As you can see, the difference is the memory allocation. So I'm running at 400, then I'm running at 200, and the last one's also running at 200, but it has this additional JVM args, which is pointing to using the JITServer. So that's what's going to happen. So let me run JMeter data at that and take a look at the graphs to see what's happening. So here's our Grafana charts showing CPU throughput. Obviously, the higher, the better. The top left here is the version of Acme Air running at 400 meg and the version at 200 meg. The top row is running without JITServer. The bottom one is running with JITServer and has been limited to 200 meg for the container. So as you can see, the one with the JITServer is ramping up the fastest. This one, the 400 is struggling initially, but it's going to eventually get to a point where it's going to be equal to the JITServer version, but it takes longer to get there. The other interesting thing to note is the 200 meg container is obviously too small. So the JVMs are pretty smart. They'll know that they're going to run out of memory, so they won't even attempt to run a lot of the JIT compiles. So it's going to be at the state for the length of this run. As you can see, the JITServer version has already reached pretty good throughput. The 400, like I mentioned, will eventually get there. Let's let it run for another 20 seconds here. So the JITServer version has reached its peak throughput. I'm gonna give another 10 seconds. So you can see the 400 megabyte version is ramping up, but it's slower. And again, it will eventually get to the point where it's efficient because it's taking time to compile those methods to get to optimized code. All right, let me go back to my presentation. We'll just let that run in the background. I could have also showed you that the JITServer itself has a number of metrics it keeps through Prometheus. So it will show you the number of connected clients. You can ask the JITServer for these using queries to get this information. It'll tell you the CPU utilization, the number of compilation threads, and the available memory it uses. So how do we use this JITServer? So basically, the JITServer is just another persona of the actual OpenJ9 JVM. So you can run the normal JVM as you typically start up any Java application, just running Java My App will run the OpenJ9 JVM. You could start the JITServer with that command, the JITServer command, and then your clients can talk to or communicate with the JITServer by using this JVM arg. There's also additional ways to configure how to run it. Full list of options is available from the Eclipse organization under OpenJ9 docs JITServer. One thing I will point out that the Java version and the OpenJ9 release must be exactly the same between the client and the server. JITServer usage in Kubernetes. Basically, you create a JITServer service that your clients can connect to. You can define and deploy your JITServer using YAML files, Helm charts. There's already a Helm chart out there that you can use to help set that up, because we know how difficult that can be setting up anything in Kubernetes. There's also a OpenShift operator, which is from OpenLiberty. So I've talked about OpenLiberty a couple of times. So that's sitting on top of the stack. So you have OpenLiberty run by IBM Samra runtimes, which includes the OpenJ9 JVM. So OpenLiberty itself comes with an operator that you can use to access that the JITServer capability. Basically, you can create a OpenLiberty application. There's a method in there or a setting you can set to say true. And so every instance of that application, when it runs, will access the same JITServer. On developer.ibm.com, there's a really good tutorial on how to use JITServer in Kubernetes. Oh, here's that in the Liberty operator, the option to turn on the JITServer. In this case, they call it the Samra Cloud Compiler. It does support encryption and authentication through TLS. Here's how you do that. It does add overhead, so be careful when you're doing that. So like that graphs I showed you a second ago with the demo, it does have a lot of metrics using Prometheus. Again, we can see the JITServer CPU utilization, available memory, connected clients, and active threads. It also has additional logging features to get more and more information on how it's running. JITServer usage recommendations. So obviously you use this when you want to compile many methods in a short period of time, which is always going to be the case when we're talking about containers. And whenever a JVM is running a constrained environment, again, containers. So this is definitely a container solution. It doesn't have to be running a container, but that's where its true power is. Network latency between the JITServer and the client VM should be relatively low, and that shouldn't be a problem if you're running in the same node on a cloud platform. It shouldn't be an issue. You definitely want to have at least 10 to 20 clients, JVMs connected to a single JITServer. Remember from the one graph we showed that the JITServer was the largest container. So you want to amortize the cost of that JITServer by connecting to at least 10 to 20 clients. And it's always better to stagger the starting of all those containers accessing the same JITServer. If they all start at the same time, you will get a little bit of performance hit. Again, encryption adds to the communication overhead, so avoid it if possible. Definitely in Kubernetes, use the session affinity bit to ensure that when a client goes down and comes back up, it's going to be using the same server. And you definitely want to enable JITServer AOT cache. Basically, when the JIT compiles a method, it'll store it in its cache. And if another instance of that container starts up and it requests the same method and the profiler says that, yes, it's the same, it'll just return that already compiled machine code. I do want to talk a little bit also about another feature of the OpenJ9 JVM, which is called Instant On. So Instant On improves startup times by 10 to almost 20%, 20 times, I'm sorry. So Instant On improves Samru Cloud Compiler auto-scaling for the JITServer. So how does that work? So Instant On is based on the Linux Cryo technology, which is basically taking snapshots of your image and then starting from that point. So you run your image, you load it, you get to a certain point, you take a snapshot, and then you save off that image. And then any future runs of that can start from that point, which is right here. And we'll start from that point. So now we're talking about Java applications starting in milliseconds as opposed to seconds. A really great feature. This came out earlier this year, and it's a core feature of OpenJ9 JVM and Samru runtimes. Here's a blog on how this works. So some final thoughts on the JITServer or the Samru Cloud Compiler. So again, the JIT provides a great advantage, but compilation does add overhead, both in CPU and memory. So the solution is we're going to disaggregate the JIT from the JVM and create a JIT compilation as a service. So this comes with the OpenJ9 Eclipse JVM. It's available now on Linux for Java 8, 11, 17, and 21 through the distribution with IBM Samru runtimes. It's especially good for constrained environments. We're talking containers and microcontainers. It is Kubernetes ready. It has its own Helm chart, Prometheus, and an OpenShift operator. It's going to definitely improve your ramp-up time and your auto-scaling behavior. It can reduce peak memory footprint, which means you can increase your app density and ultimately reduce the cost. And when combined with Instant On, obviously you get extra great performance. And most importantly, it's a Java solution to a Java problem with no compromise. So initially we talked about that sweet spot and a lot of innovation happening around trying to solve that problem. And what I'm going to show here is that this particular solution is a straight Java solution. So let's take a look at a typical Java application. It has full support of all the Java APIs available. It has dynamic Java through reflection and creating dynamic objects. It has a real efficient garbage collection to the JVM, and it has that JIT optimization, of course, right? The longer it runs, the better it runs. But when we're talking about containers, we do not get minimal container size. We have slow startup time and ramp up time. Another concept I want to introduce briefly here is dev prod parity. So this is one of those, if you're familiar with the 12-factor app methodology for cloud native apps, dev prod parity is one of the guidelines they use, or best practices they recommend. And that is basically ensuring that your development and your testing and your production environments are as close to the same as possible. So you reduce the chance of errors creeping in along that line. And in standard Java, this is pretty easy to do. Now let's talk about some of those images some of the solutions I talked about earlier. A lot of them have to do with native image, which is statically compiling your Java application. So what you get from that is you get a real minimal container size. You get a very small container. You get great startup time. But what you're losing is that you don't have access to all the Java APIs, all the dynamic features of Java you can't use. Obviously, with no JVM, you don't get any garbage collection or JIT optimization. So the state of your executable code is going to stay the same no matter how long it runs. Ramp up time really isn't an issue anymore. Dev prod parity. So the chances of you adhering to this are going to be lower in this environment, especially if we go off and we start, if you're a developer and you're going through that iteration phase of testing, you're probably not going to take time to do a recompile and a static compile and rebuild your environment every time you make a change. You're probably going to take advantage of, you're writing Java code, you're going to take advantage of the JVM. So that just introduces potential issues. It's not as easy to adhere to that dev prod parity. And then finally, we're going to talk about this solution I talked about today, which is JITServer plus instant on. So in that case, you're going to get all the features that you get with typical Java application development, all the benefits of running Java and why Java is so popular. On top of that, we will now get minimal container sizes. We will have millisecond startup time, and we'll have ramp up time vastly improved to the point where we can reduce those containers and we have efficient scaling. So I talked a little bit about Open Liberty. I'd like to point you to this slide here where we have a lot of good information about modernizing your applications through the Open Liberty, which is a Java runtime. One really cool feature about the openliberty.io website is they have a section called Guides, which allows you to learn some of the newer Java technologies, especially around microprofile and Hagarty EE. And you can do that through the hosted, the service is hosted on IBM Cloud, so you don't have to install anything on your own machine. You just need to log in. You go to the IBM Cloud through these guides, you get an IDE and a tutorial where you can try these things out. And there's a ton of them that take about 15 to 20 minutes each to complete. Really a cool feature. Whoops, I hit the wrong button. Speaking of that, we also have some great tools about modernizing your application. If it's currently a monolith on WebSphere Application Server or WebLogic or JBoss or Tomcat, we have tools to help you isolate or figure out how to break up your monolith to get into using microservices. Some more links to some good information on some of the top things I talked about today. And with that, that is the end of my talk. Now, this QR code will take you to my SlideShare site where you can find the slides for this particular talk and just look for JCON World 2023 and you'll find it there.